Now let's have some further application of the first and the second derivative of a function. Now let's start with the first derivative. So we're saying that the first derivative at this point x, at the x value here, would give us a gradient of the tangent of the curve at that point. And the same thing here would give us a gradient of the tangent at the curve at that point. And it goes on and on. Just find the first derivative and substitute the x value in there. And we will get the gradient of the function at that point, or the instantaneous rate of change at that point. Now if you look here, you notice that the gradient of the tangents on this side are negative, and the gradient of the tangent on this side, of the tangents on this side here, are positive. What that is implying to us is that for every value of x, and let's say that we're going to split this curve in two, for every value of x on this side of the curve, the function is decreasing, and for every value of x on this side of the curve, the function is increasing. So in other words, if I wanted to find the value of x for which a function is decreasing, all I would need to do is just say to differentiate the function, find dy by dx, and then solve for the value of x for which the first derivative would be less than 0. And to find the value of x for which the function is increasing, the first derivative would be greater than 0. Now, let's look on this little thing right here. We have the same curve, right? And now we're not going to be looking at the tangent that has a negative gradient. We're not going to be looking at the tangent that has a positive gradient. We're going to be looking at the tangent right here. Now, forgive me. You know what? Let me draw it properly. I will not tell you that this is not drawn to scale, even though it is not. It's not drawn to scale, but let me see if I can draw it as best as possible. So, we are drawing this line and it is tangential. Yes, right there. So notice that this line is a horizontal line. The gradient of this line is 0. Now, what this is implying to us is that this point of tangency here is neither a point of positive gradient or negative. At that point, the function is neither increasing nor decreasing. We call that point a stationary point. So, what we have covered so far would be the fact that a function is decreasing for values of x for which the derivative is less than 0. It is decreasing. dy by dx is less than 0. If dy by dx is equal to 0, then it is a stationary point. If dy by dx is greater than 0, then for those values of x, it is an increasing function. We'll look at an example soon to make this more concrete. But before we do, let's look on the fact that there are actually two types of stationary points. And let's change the color. So we could either have a stationary point at the lowest point on the curve or the highest point on the curve. The fact is, though, there's a limitation of the first derivative. The first derivative tells us that for an x value, this is a stationary point. At this point, the first derivative is equal to 0. However, the first derivative does not tell us whether it is a minimum or a maximum point. To determine whether or not it's a minimum, we use the second derivative. So what we're going to do is that we're going to take the first derivative and we're going to differentiate it again. Or rather, we're going to take the first derivative and we're going to differentiate it. So we looked at the first derivative being greater than, less than, or equal to 0. And we looked at the second derivative being greater than and less than 0. Now, just to point out to you, there's one little last application that we left out, and that's the second derivative being equal to 0. So let's say here, we have this curve on the Cartesian plane. It goes up, down, up, down. Now that's our curve. Let's change the color. Now notice that for this curve, let's start over this side. The gradient is increasing, increasing, stationary, decreasing, decreasing, decreasing. We say that this section of the curve is concave down. So you can see that a curve would be concave down if it is increasing and then decreasing. Now, notice here that it continues decreasing, decreasing, decreasing. Point of stationary point, increasing, 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 increasing. So it switches from increasing to decreasing, meaning that it's concave down, to decreasing to increasing, meaning that this is concave up. Now, the fact that a curve switches from an area of being concave down to being concave up, the point of change of concavity, which is this point, is called the inflection point. That is the inflection point. We find a possible inflection point by taking the second derivative and equating it to 0. Whatever x value we get, then that is a possible inflection point. So now that we know the application of the first derivative and we know the application of the second derivative in terms of there being greater than, less than, or equal to 0, let's do a problem.